Okay guys, in this video we're going to look at a couple of examples of just evaluating matrix expressions using our order of operations and using the three basic operations that we've already seen, which are addition, subtraction, and scalar multiplication. So taking a look at this example here, I've given us a couple of matrices A and B here. You notice that they are the same order. Let's go ahead and write their order in the bottom right corner. We say 2 rows by 3 columns. We say 2 by 3 and 2 by 3. And so our goal here is to just evaluate for these expressions. So one thing that we mentioned in the last video that I want to re-mention here is essentially that when we use the order of operations for matrices, maybe not all of these operations are defined, but certainly multiplication is always going to come before addition and subtraction. So that includes matrix multiplication, which we'll cover soon, but also scalar multiplication always comes before addition and subtraction. So looking at these expressions here, given the two matrices up here, 3a minus 4b, let's go ahead and take a look at how you would maybe work with such an expression. So we say 3 times the matrix A, which is this, 1, negative 2, 4, okay, 3, 2, and 10. And we're going to take away 4 times the matrix B, which is negative 5, 5, and 1, okay, and then 1, 2, and 8. And so as I have in the past, I've mentioned that the best thing to do is to rewrite this as add the opposite. And so what I mean is, if you have subtraction, we're going to change this negative to a positive, and then I'll just change my positive 4 to a negative 4. And so we can just distribute a negative 4 throughout all of this and add that on, as opposed to take away 4 times, a positive 4 times all of this. And so let's go ahead and, using our order of operations, take care of our multiplication first here. And so distributing the scalar 3 through this first matrix, it looks like we would triple all of our numbers. So we'd get 3, negative 6, 12, okay. This would become 3 times 3 is 9, 3 times 2 is 6, and 3 times 10 is 30. And then over here we're going to keep this as a plus, right? We wanted a plus, but we're going to distribute a negative 4 as opposed to a positive 4 by adding the opposite, right? So we say negative 4 times negative 5 is positive 20. Negative 4 times positive 5 is negative 20, and negative 4 times positive 1 is negative 4. Okay, negative 4 times 1 is negative 4. Negative 4 times 2 is negative 8, and then negative 4 times a positive 8 here is a negative 32. So with these being multiplied out now, you see that we can go ahead and add these component-wise. Since they are indeed the same order, we can add them, or at least addition is defined. So we're going to add component-wise 3 plus 20 here, give us our 23. Negative 6 plus negative 20 is negative 26, and then 12 plus a negative 4 here is an 8. And then going down our second row first column entries, we say 9 plus a negative 4 would give us a positive 5. This 6 plus a negative 8 here would be a negative 2, and then 30 plus a negative 32 would be a negative 2. So this entire expression here, its simplified form would be this 2 by 3 matrix that we see here. So taking a look at letter B, this is kind of an interesting situation, because we're looking at a situation in which, at least with our order of operations, we have some parentheses involved. And so there is actually a little bit of leeway that we can use here. We could actually distribute this scalar throughout, but what I want to do is look at a situation where maybe let's just go ahead and work with our order of operations, which means we're going to end up doing what's in the parentheses first here. And so let's go ahead and rewrite all of this here. We say 2 times in parentheses, now our matrix A, right, that was 1, negative 2, 4. 1, negative 2, 4 on the first row, 3, 2, 10 on the second row, 3, 2, 10. And then this is minus 2 times the matrix B, which was negative 5, 5, 1, 5, 5, 1. And then we had in the second row 1, 2, 8, 1, 2, 8. And so we'll end our parentheses. So because parentheses take precedent over many things here, we're going to go ahead and start by evaluating for what's in here first. And so I noticed that I want to distribute my negative 2 here. Now before I do that, I'm going to change this negative, the subtraction relationship, to adding the opposite, which means this 2 here, I'm going to put a negative on it. We're going to say plus a negative 2. And so doing what's inside the parentheses, I'd have to multiply this scalar through first. So we're going to rewrite everything here. We say 2 times in parentheses. Now we didn't do anything to this first matrix yet, so we're going to rewrite it. So we say 3, 2, 10. And then this is plus still. Now we're going to take everything over in this matrix times this negative 2 scalar. So that means that we're going to get a positive 10, okay, a negative 10, and a negative 2 here, as well as a negative 2, a negative 4, and a negative 16 here. And then I'll put my end parenthesis on here. So before we distribute our 2 throughout, let's go ahead and evaluate for what's in the parentheses. That is to say, let's go ahead and add these two matrices together. So now we can do this. It is defined because they do both have the same orders. So we're going to get a new 2 by 3 matrix here. in which we add component-wise, like 1 plus 10 here is 11, negative 2 plus negative 10 is negative 12, and then 4 plus negative 2 is a 2. 3 plus a negative 2 is a 1, 2 plus a negative 4 is a negative 2, and then 10 plus a negative, and this is a negative 16 here, 16. 10 plus a negative 16 is a negative 6. So now all we have to do, looks like, is scalar multiply by a 2, meaning we're just going to double all of our initial entries. So we get this final simplified 2 by 3 matrix that comes out to be just all these entries doubled. So we get a, like a 22, a negative 24, and a 4, and then we would get a 2, a negative 4, and a negative 12. So evaluating these expressions, just remember to use your order of operations